All right, so we're going to start with the alpha carbon. What type of substitution do we have on this alpha carbon? Primary, secondary, or tertiary? Secondary. So we go to the row for secondaries in the table on page 3 of the SN2 handout. And it's good that you're labeling the alpha carbon. That's an excellent habit. Now, who is our nucleophilic atom?
The oxygen, the neutral oxygen.
That's right. We can't just say oxygen, we have to say neutral oxygen, because oxygen with a negative charge would give us a totally different answer on the right-hand side. So if you find the neutral oxygen, I think it has a column all to itself in the table, and that would tell us secondary and a neutral oxygen would be SN1/E1.
Yes.
But as we've discussed, the E1 is actually much less important than the SN1, so we're still just drawing the SN1 reaction here. There would only be about 5% E1, so we'll hold off on that still. We'll get to that later. Okay, so you showed the leaving group leaving and the nucleophile coming in. All right, and here's where we started to have a couple of issues. First issue is the most important part of any picture is the charges. So anytime you do any step, you have to change 2 charges. Or maybe I missed it, but it looked like you missed the charges on this intermediate over here. What's wrong with, who has a charge that we haven't put in there? Maybe you put it in and I didn't see. So I'm looking at this picture here.
That's an intermediate right there?
This one here?
Yeah.
So this is the intermediate that you get when the water attacks, right?
I forgot the positive on that.
Okay, right. And it seems like a minor detail, but really the charges are the most important part. So we got to put that charge in because this oxygen was at the initial tail.
Correct.
For the same reason that you made this into neutral, the oxygen should be positive. After all, the next thing you did was the deprotonation, right?
Yes.
But nature wouldn't even bother deprotonating if it weren't for getting rid of this charge. The only reason we're deprotonating is to get rid of the charge. So that's actually a pretty important thing to put in. Now, there's another issue here. When the water attacks this carbon, is it forming a stereocenter?
Correct.
Yeah, it is. So we have to show wedges and dashes, which you correctly did. Now, how many products are we going to get here? How many stereoisomers? 1 or 2?
2.
All right, well, it looks to me like you only drew 1.
I did.
Okay. So that was an issue. All right, so that means that you only maybe get half credit for the problem. We have to draw all the possible products here. So you drew the product where the water ends up on the dash.
Yes.
But the other product would be where it ends up on a wedge.
Okay.
Good. Okay. That's one of the main issues they'd be looking for on exams, so we want to get into the habit. Now, how do you know that the water is going to end up, how do you know the water is going to be attacking from both directions here, both from in front and from behind? With SN2, we only got 1 stereoisomeric product. So why should we get 2 stereoisomeric products with SN1?
Because we're not concerned with steric hindrance. It's the charge that we're dealing with.
Okay.
They can attack from either way.
Yeah, that last thing you said was the key. Let's review molecular geometry. What is the molecular geometry of this carbon? Tetrahedral, trigonoplanar, linear? What's the molecular geometry of the original alpha carbon?
Tetrahedral.
Because it's attached to 4 things. But what's the molecular geometry of this carbon?
It's trigonoplanar.
Because now it's only attached to 3 things. Carbocations are always trigonoplanar, and planar is just a fancy word for flat. Well, like my hand is flat. Well, when something's flat, you can generally attack it from either direction. You can attack from this side or from this side. So as a general rule, anytime you have something attacking something trigonoplanar, you're going to get a maximum of 2 products. Anytime you're attacking something trigonoplanar, you're going to get a maximum of 2 products. And here's the 2 products we got here. Are we going to get more of one of these, or are we going to get equal amounts?
You're going to get equal amounts.
Because there's no real reason to prefer one side of the trigonal plane to the other side. This is what's called a racemic mixture. It's a key fact about SN1 that it gives us a racemic mixture. That just means equal amounts of both enantiomers over here. Why didn't we get 2 products for SN2? Because in SN2 we were attacking something tetrahedral. In SN2 we never formed the carbocation. In SN2 the nucleophile is attacking something tetrahedral, and there, as you were kind of mentioning, the leaving group blocks one of the roots. The leaving group blocks, say, the front side attack, so the nucleophile has to come in from the back side. So there's a very important difference between stereochemistry for SN2 and SN1. That's one of the main issues that would be tested on the exam. SN2 gives you only 1 stereoisomeric product with an inversion of configuration. But SN1 gives you 2 products in generally equal amounts because we're attacking something trigonoplanar. Okay, and then you did your deprotonations. In order to show that correctly, you got to break off one of the hydrogens, so you can draw an arrow coming into it. also happen down here.
Okay.
And that gives us our two final products. One where the OH is on a wedge and one where it's on a dash. So technically speaking, to show the full mechanism, we'd have to show, at this point, we get into it with two different intermediates. Now there's two different paths. Eventually people get bored with this and they don't necessarily draw both paths here. But at the very start, when you're first learning the material, it's a good habit to show these two different paths. Okay. So that would give us this. Okay, so for the most part, you got through this with no trouble, but the key issue here that we were missing was an SN1 can give you a maximum of 2 products if you're forming a stereocenter. Now, if you recall, we just did another SN1 a couple minutes ago, and we only got 1 product. Why did that previous SN1 we did a few minutes ago only give us 1 product? Because we weren't forming a stereocenter. If you're not forming a stereocenter, then you only get 1 product because there are no enantiomers. But if you are forming a stereocenter, then you're going to get the 2 products, and that's one of the issues that the tests are designed to test. Okay, and again we had our deprotonation. And the other issue was we can't forget to put in the charges. That's the reason we're deprotonating. Okay, good. Oh. By the way, something you might have noticed is this is the same problem as before. Notice that in this case I put the water above the arrow. Do you know, what does it mean when we put a reagent above the arrow? What does that signify?
That it's in the solvent?
That it is the solvent.
It is the solvent.
Yeah. Now actually it's unfortunate. Sometimes it doesn't signify anything.
Sure.
Sometimes people just write one of the reagents above the arrow for no reason.
Okay.
However, a lot of the time when you write the reagent above the arrow, it means that that reagent is the solvent.
Okay.
All right, and that's what I was trying to convey here. After all, we need a solvent, and water is a good solvent. So this is conveying that water is the solvent here. Sometimes we also put catalysts above the arrow, but here this is the solvent. Anyway, the important to notice is it didn't make any difference that this was the solvent. A solvent can participate in reactions just like any other reagent, so it really doesn't make much difference whether something's the solvent or not. However, it's good to know this reaction here then would be called savolysis. Savolysis. You can see savolysis is just an SN1 reaction where we use the solvent as the nucleophile. It's not even all that important to know the name because it's just an SN1 reaction. The only difference this makes is that if you're using the solvent as the nucleophile, that probably helps the reaction because we've got lots and lots of solvent. We'll have to worry about running out of solvent here. Okay.
Sometimes problems have something else below the arrow.
Sometimes that's the solvent.
Yes, okay.
Yeah, maybe, so oftentimes maybe they'll put the reagent above the arrow and then they'll put the solvent below the arrow. There's a bunch of different conventions, but yeah. Okay, now suppose that instead of starting with this starting material, suppose this had been the starting material. Just describe to me in words, what would our final products be?
Well, you'd have stereochemistry once again, so you get 2 products of racemic mixture, and it would be, you could draw the exact same diagrams. Or,
so yeah, so what would the final products be? All I meant was, I just wanted to make sure that you're recognizing they'd be the same.
Oh, okay.
Yeah, I just wanted to make sure you're recognizing, it doesn't matter whether the iodine starts out on a wedge or a dash, right? Before I had this on a wedge, and we got these 2 products, and now we have the starting material with the iodine on the dash, but we get the same 2 products, right?
Correct.
Why doesn't it make any difference? Because after the iodine leaves, this is just going to be trigonal planar anyway. It doesn't matter whether the iodine leaving group starts off on a wedge or a dash. After it leaves, this is just going to be a flat plane anyway, and then you can attack from either direction. This one's a little bit of a trick question. Let's try to predict what's going to happen here.
It's going to be it's going to be no reaction.
Okay, good. That's why it was kind of a trick question, but you picked that up. All right, good. Yeah, you're right, no reaction. How do we know? Well, it's good that you labeled the alpha carbon and you saw that it's primary. And the beta carbon is not tertiary, so we should just be in the normal row that says a normal primary alpha carbon. So again, we're looking at the table at the bottom of page 3 of the substitution and elimination handout. So you saw that that would just be, so we're in the second row of the table for primary. And who is our nucleophilic atom?
The neutral oxygen.
Neutral oxygen. Again, it's important to point out that charge. Well, you can see that that would give us no reaction here.